Thanks for the very nice introduction. So I will tell about quantum computing, which is the thing on which I have been working for 18 years, and its implications on information security. Oh, oops. So quantum computing combines quantum physics with computing. Quantum physics is a part of physics that studies the laws of nature on the level of individual atoms and particles. At this level, nature is somewhat different from what we see in our everyday lives. And quantum computing attempts to use these different laws of nature for computing and communication. For example, to do faster computation or to do more secure data transmission. And here are the two most famous achievements of quantum computing. So if we build quantum computers, there will be many things that they can do faster than ordinary computers, but there are two that are particularly famous, and one is factoring large numbers. So let's say that we have a number that is a product of two smaller numbers. We are given the large number, we have to factorize it into two smaller numbers. If we are talking about numbers with 300 digits or so, then conventional computers are too slow. There is simply no good methods for factoring large numbers on an ordinary computer. And in contrast, if we built a quantum computer, they would be able to factor very large numbers efficiently. And second famous thing for which quantum computers would be better would be searching large amounts of data. So let's say that we have a large number of objects, and we want to find an object with a certain property. And the only operation that we can do is looking at an object and seeing, is it the right one? Well, it wasn't. Is this the right one? Yes, it is. Now, if we have 1 million objects, and only one has the right property, then on an ordinary computer, there is a chance that ordinary computer will have to look at all 1 million objects. And quantum computer will be able to do better. It will be able to search among a large number of objects in time that is roughly square root of the number of objects. A very simple illustrative example for this is searching in a phone book. Let's say that we have a phone book, and this phone book is indexed by people's names, and as phone books typically are, it's not indexed by numbers. And we would like to do a reverse lookup. We have a phone number, we would like to find a person to whom it belongs. So if there is no indexing by phone numbers, then the only thing that we can do is to look at various entries in the phone book until we find who has this number. And if it's a phone book with 1 million entries, then in our ordinary world, we would need 1 million steps until we find the right phone number. But if we had a quantum computer, that million would suddenly go down to square root of 1 million, which is 1,000. And more broadly, the same thing would happen for any search task. If we have a search task which we could solve on an ordinary computer by examining 1 million possibilities, we would be able to solve it on a quantum computer by examining just 1,000 of them. And here is how a quantum computer might actually look like. So this is the first prototype of a quantum computer that was built 11 years ago. So in this prototype, a quantum computer is a molecule swimming in a liquid. And atoms in this molecule have a property that is called nuclear spin, which essentially determines how this atom spins in a magnetic field. And a spin is essentially a direction. A particle can be spinning upwards, downwards. it can be spinning in some other direction. So we encode information into a nuclear spin, and then we manipulate spins by turning magnetic field on and off. And in this way, we can build a quantum computer. And this has been done. This is a very small quantum computer into which we can encode 13 bits of information, and we can demonstrate that the basic principles indeed works, and that this device computes the way it should. Now, 13 bits is way too little to do any useful computation that cannot be done on a classical computer, but we can illustrate that the principles work. Now, let me move on to my main topic for today, which is how the quantum computers would affect information security and cryptography. If we think of usual or symmetric encryption, it works in this way. We have a secret message. We encrypt it with the help of secret key. We get an encrypted message. We send it. The person on the other side decrypts it, and he gets back the thing that we sent. If someone in the middle is listening, he only sees the encrypted message, and without knowing the secret key, this message is useless. So encryption methods like this have been around for a long time. Well, Enigma machines that German army used in World War II are example of this paradigm. And the things that we do on our computers are still the same paradigm, except that operations that we use and the amounts of computation that we do are much larger. And a typical code-breaking scenario is that we have the encrypted message, we saw it, and what we actually want is we want the secret key. So knowing one secret message gives us some information. Knowing secret key enables us to read everything that is encrypted with this key in the future. So it can enable us to read thousands and thousands of more messages. So the typical code-breaking scenario is what is known in scientific literature as a known plain text attack. Is we have the encrypted message, and we have somehow managed to get hold of one message how it looked like before encryption. For example, we might have guessed this message. We might have used some human engineering tricks to get it out of the person who encrypted it. We might have done key logging. We have done something, so now we have a pair of messages. We know this is how a message looked before encryption. This is how it looks after encryption. We want the secret key so that we can read all the other messages. And typically, encryption algorithms are pretty good, and they are designed so that usually about the best strategy for getting secret key is testing all the secret keys possible. The purpose of designing a good symmetric encryption algorithm is to defeat all the attacks beyond trying all possible keys. So if we have n keys, classically on our ordinary computer, we would have to try them all. But if we had a quantum computer, we would be able to search among n possible secret keys in time that is just square root of n. So for example, for 64-bit keys, the number of steps to search amongst them would go down from this on a conventional computer to this on a quantum computer. And this is quite a dramatic change. On the other hand, one can defeat this by doubling our key size. If we make our secret keys twice as long, what used to be the number of secret keys is now the square root of the number of secret keys. So quantum computers provide an advantage for code breaking, But this advantage can be defeated just by making the secret keys twice as long. Now, there is another very important aspect of cryptography, which is key exchange. If I am communicating on an internet with an internet shopping company, I need a secret key to communicate my information to them. And typically, if I'm shopping with them for the first time, I don't have a secret key. So what one needs to do is one needs to establish a secret key over the internet so that someone who is listening to our conversation doesn't learn this secret key. And this is indeed possible. There are protocols for key exchange, which we can run. And at the end of protocol for key exchange, the parties on the two ends end up with secret key. The person who is listening in the middle does not learn the secret key. Instead, he learns some bits of information, and getting secret key from those bits of information is possible in principle, but corresponds to solving difficult mathematical problem. So the way how a lot of our secret communication on the internet goes on is we use key exchange to establish secret key, and then once we have the secret key, we can communicate. And here is where the quantum computing comes in big time. Breaking the protocols for key exchange that are currently being used corresponds to mathematical problems like factoring a large number, which is what I had on my third slide, or solving something that is called discrete logarithm problem. And both of those problems have the property that they are difficult for ordinary computers, but they become easy for quantum computers. So if someone built a quantum computer, he could use it to break the key exchange and to prevent people from establishing secret keys over the internet. So the short summary about impossible impact of quantum computers on cryptography is that ordinary encryption is essentially safe, but key exchange is broken, and so is public key cryptography, which is kind of similar to key exchange. So now let me talk about how far people actually are with building a quantum computer. So the way quantum computers would work is they encode information into quantum states. For example, we might encode 0 into an atom that is spinning upwards and 1 into an atom that is spinning downwards. And then we get a basic information unit of quantum computing, which is called quantum bit. It has two states, quantum 0 and quantum 1, and then we can take quantum bits and we can build quantum computer out of them. One of quantum computer experimentalists has divided building a quantum computer into 7 major steps, starting with operations on single quantum bits. This has been done for a while. Then next step is doing some algorithms on multiple quantum bits. This is also done. The next stage is starting to do quantum error correction and quantum control. And then there are more and more steps, at the end of which we end up with a full-scale quantum computer. So at the moment, we are at roughly middle of step 4. So building quantum computer has been going on for about 15 years. We are roughly halfway through this pyramid. We know how to build quantum bits quite well, but quantum bits are susceptible to errors. And no matter how well we build, at some point there will be errors happening, so we need to build up mechanisms for error correction. And this is what people in labs are working now, building quantum error correction and using quantum error correction to build devices that preserve information longer than an individual quantum bit could do by itself. There are many ways how we could build quantum computers. Basically, this functionality of quantum bit, quantum 0 and quantum 1 is quite universal across many subfields of quantum physics. When I started reading about quantum physics, I opened a quantum physics textbook, and I was surprised to see how many things there were that were described in textbook that were essentially quantum bits. So there are many technologies based on which one could build quantum computers. And at the moment, there are several of these technologies which one has demonstrated experiments with up to 10 quantum bits and showed that the basic principles of quantum computer work. Now, the big challenge is scaling this up from these 10 quantum bits to the scale at which quantum computers would actually be able to do useful computations. And at the moment, the most promising technology is superconductors. So superconductors are materials that conduct electricity with no resistance. And this typically happens at very low temperatures, close to absolute zero. At these temperatures, many materials lose electric resistance, and the electric current starts moving across them with no resistance. And the reason why this happens is that at these low temperatures, the whole electric current forms one big quantum state. Millions and billions and trillions of electrons merge into one very big quantum state. And we can encode information into this quantum state and use it to compute. So, for example, what we could do, we could encode 0 into electric current that is moving on a superconductor in one direction, for example, clockwise, and 1 into current that is moving counterclockwise. And on this platform, a group at University of California, Santa Barbara has showed that they can do individual quantum operations with precision that is well above 99%. So they have 9 quantum bits, and they can do operations on them with really high precision. And there is one big advantage that this technology has. The devices that they use are something that can be microfabricated by the standard integrated circuit techniques, because these are essentially standard integrated circuits which you cool to very low temperatures, and then they become superconducting, and you can operate with them as a superconductor. So there is a hope that if they have built 9 of them and they are working well, then the standard techniques for microfabrication would make it easy to scale it up to thousands, tens of thousands, or hundreds of thousands. There is nothing that has to be fine-tuned for every quantum bit individually. It's something that can be fabricated on a large scale. So this is the next challenge. And at this point, we are starting to see quite a bit of interest from various large companies. So for example, Google has partnered with this group at University of California, Santa Barbara to build a quantum computing together. What this means is that they have hired part of this group, and part of this group is now working in Google, and they have access to Google's resources. And there have been more big headlines about quantum computing in major companies over the last year. Intel is investing $50 million into Delft University of Technology, who is also doing a very large-scale effort to build a quantum computer. And Alibaba, which is the Chinese counterpart of Google, has pledged to invest 30 million Chinese yuan per year. So suddenly we start seeing large projects on quantum computing that are devoted to building large-scale devices that would actually do something sizable. So the future outlook is this. We already have high quality components. We hope it's possible to mass manufacture them. So these two things together, they make it plausible that we might have some form of quantum computer in 15 to 20 years. And some people are even more optimistic. There are some scientists that are promising a working quantum computer in 10 years. Well, I would not dare to do that myself, but some people are doing that. Now, if we go back to the implications for information security and cryptography, an attacker can store encrypted information now, even if he doesn't have a quantum computer. And then once he has a quantum computer, he can decrypt that information. And then he has our secret data. And it is well known that a lot of data need to be secure not just for a day or two, but for years. So it seems that the time to start thinking about how cryptography would look like after quantum computers is approaching. And for scientific community, probably this time is now, because it takes a while until scientific community comes up with schemes, until they are tested, until they go to industry, until they are standardized. There is a lot of work between an idea for a new scheme and this new scheme being in practice. So for scientific community, time to think about cryptography that is secure against quantum computers is now. And we call this post-quantum cryptography. Cryptography that survives quantum computers. And I mentioned that symmetric encryption is kind of safe. So now when I talk about cryptography, I mean key exchange and public key cryptography. So the good news is that actually there is a lot of candidate alternatives to the cryptography that we have. In order to have key exchange or public key cryptography, we need to have a difficult mathematical problem, and then we need to build a scheme in which code breaking would correspond to this difficult mathematical problem. Now, there are actually quite a few ways how one could build key exchange or public key cryptography based on mathematical problems that seem to remain safe against quantum computers. One can base schemes on mathematical structures that are called lattices. One can base schemes on error-correcting codes. One can base schemes on multivariate quadratic equations. In each of those cases, people already have candidate schemes for replacing schemes that will be broken by a quantum computer. And some of those schemes are actually quite old. The oldest one of them dates back to 1978. So it has been around for a while, except that before the threat of quantum computers emerged, people didn't really see point in this scheme. So it was somehow existing in the community of theoretical cryptography, and nobody really thought of putting it into practice that much. Now, there is a reason to do that. Some of those schemes have some performance issues that have prevented them from being put into practice. One issue that is common to quite a few of them is the key size. So if we think of methods that will be broken by a quantum computer, then a typical key size is a couple of thousand bits. For the replacement, the key size would range from roughly the same for some schemes to, say, 30 or 70 megabits for some other schemes. Now, this is possibly not a practical scheme if we have to send secret keys somewhere. Particularly if we wanted to use it on devices with low bandwidth. So the point that I'm underlining here is that some of those schemes have performance issues, But we see that in some cases, those issues are actually solved. And there's definitely more research needed into security of those schemes. The two leading candidates are schemes that are based on lattices or error-correcting codes. And the common feature for both of those schemes is that these are actually families of schemes. There are many lattices that one can use. There are many error-correcting codes that we can use. Well, you don't need to know what lattice is. Just take my word that there are many possibly usable lattices known. And the thing is, the security depends on which lattice or which type of error-correcting code you take. For some families of lattices or error-correcting codes, these schemes have actually been broken. In the other cases, they seem to be secure. The exact boundary between the lattices and codes for which they are secure versus for which they are not is something a bit fuzzy, and we don't yet feel it very well. And often, we want to make our schemes more efficient, and there is a trade-off. If we choose simpler lattices or codes, schemes become more efficient. We can do encryption faster. Security goes down. And one needs to find the optimal point on this trade-off between security on one hand and efficiency on the other hand. And there is a very nice cautionary story that came out maybe a year ago about a scheme called Soliloquy, which is a lattice scheme that was invented by British intelligence headquarters. And their goal was to make a lattice scheme that would be really efficient and simple to use. It ended up to be broken by themselves. It's not a story about intelligence agency giving a scheme to the world with a loophole. It's a story in which intelligence agency tried to design a scheme. They broke it. They told the story to the world to caution the world. So to summarize, well, we have been making substantial advantages towards quantum computers. And if we manage to build one, it will obliterate the existing schemes for key exchange and public key cryptography. And the time for scientific community to think about the replacements is now. And scientists have been thinking about it. Thanks.
Yes, thank you a lot, Andris, personally, from all the people of Latvia for making Latvia a center for quantum computing. For those of you who don't know, then there is a European-funded research project of about 1 million, I think, and the center where it's coordinated is in Riga. Personally, thanks to Andris. So I think there was one question, yes? But yes, we cannot take very many questions, but a few we can, maybe, because we are started on time.
Okay. Thank you for this presentation. It's very nice. And yes, as we know, quantum computing is now the future. And just a question, so because we are in this conference for security, so it means that use of quantum computer in the future would ensure the better security of data. Is like this or not?
Well, it actually goes both ways. We can use quantum computing to ensure better security, and we can use them to break codes.
Yes, one or two, because it's like say that quantum information is not possible to be copied.
Yes, yes.
It would be the key to ensure the security for data.
Yes, that's the other side of quantum computing that I didn't touch. One can also build secure data transmission schemes that are based on quantum effects. And then those schemes would be perfectly secure. And that's also something that has been happening.
And the question actually is why it's not possible to copy this information? I mean...
why?
Yes, why?
Well, somehow the laws of quantum mechanics don't permit it. It's well, like a simple example would be this. So think of this atom spin that is pointing in some direction. So laws of quantum mechanics permit it to measure whether it's pointing up or down, but they don't permit to measure the direction completely. So we can choose to measure it up or down, but then if it's in some middle direction, we don't learn that it's in some middle direction. We get an answer that it's pointing up or down, and we destroy this middle direction. So this...
I have the following question about size we need for quantum computers. Is there some fixed size to which we need to grow quantum computers to solve some problems, or more complex problems will require building more complex quantum computers to solve them?
Well, I guess it depends on what we want to solve. So I think the threshold for useful quantum computers is around 100 quantum bits. At this point, we would be able to do some interesting things with chemistry simulations. And then the quantum computers for code breaking, which I mentioned in my talk, that would probably require a few thousand quantum bits.
But the trend is that if we invent really difficult problem, we will need really big quantum computer, or is this stopping at some point?
Well, there is a hope that we might invent problems which are difficult even for quantum computers, because quantum computers don't solve everything. What happens is that they provide big improvement for certain specific tasks. And there are also computational tasks for which quantum computers provide no advantage whatsoever. So the advantage over, depending on the task that you are doing, the advantage over a conventional computer could be huge, or it could also be none. So what we want is to base our security on things for which the advantage of quantum computing is close to that.
So basically, is this true or false, that if we build 2 times quantum computers 2 times the size, will it solve something too fast bigger, 2 times faster, or no, or this doesn't correlate?
Well, it depends on the computational task, as with ordinary computer.
Could you name some of those things that quantum computers don't do, where there's the non-difference? You mentioned that there are computational tasks where the difference between quantum computer and standard quantum is none. Could you name some examples, please?
Well, so example for which I don't know the difference is multiplying large matrices. Well, another example is any task for which you have to read all the data and for which you already have a conventional algorithm whose running time is close to time, but you need to read the whole data.